Because I know that something in my necklace we can see all that.
Went to the wrong building.
I wonder whose chair will break this time. Every time I've been in here, the chair has broken in there. I hope it's not mine. Literally, the chair's breaking.
Good morning. Can you hear me? I'm Dr. Will Harris, a departmental colleague of our speaker this morning. This is the first time someone has given a second Cawthorne lecture. Dr. Homer White stood in for Dr. Jack Birdwhistle 5 years ago after Doc's untimely passing and delivered a very fine talk then. I'm pleased that Dr. White is here to speak again on his own behalf after being named the 2019 Don and Chris Kerr Cawthorne Excellence in Teaching Award winner. Dr. Homer White has taught at Georgetown College since 1996. Before coming here, he obtained a bachelor's degree from Princeton University and a doctorate in mathematics at the University of North Carolina at Chapel Hill. And he spent 5 years on the faculty at Pikeville College here in Kentucky. Dr. White is the prototypical restless academic. His ergodic theory, studying the long-term statistical behavior of dynamical systems, but over time, he has veered first into the history of mathematics, studying both papers of the famous Swiss mathematician Leonard Euler, written in Latin, and those of pre-colonial Indian mathematicians, written in Sanskrit. More recently, he's delved into data analysis, obtaining a master's degree, recent sabbatical leave, to help him prepare to teach our current computer science course offerings. Additionally, he has taught classes during his time at Georgetown in Eastern philosophy, astronomy, and Ashtanga yoga. Perhaps the most gratifying aspect of being involved with assembling Dr. White's nomination for this award was getting to see the nice things that students and colleagues had to say about him. I'll limit myself to several descriptors in one lengthier comment. The descriptors included enthusiastic, most knowledgeable, loves teaching, innovative, prompt with feedback, and caring. As for the passage, it's from a former student. He is both a staggering intellect and a passionate promoter of his subject matter, who inspires curiosity in his students and serves as a model of academic excellence, encouraging students to achieve more than even they think they're capable of. He does this all while being kind, calm, and patient, with an office door that's always open. Georgetown College has many, many excellent and caring teachers. But today, we are here to honor the service of Dr. Homer White by listening to his Cawthorne lecture on Between Science, Art, and Religion, the Liminal Life of Mathematics.
So thank you, Dr. Harris, for your kind introduction. And I also appreciate well, so there's a thing when you nominate somebody for a Cawthorne Award, you kind of sneak around for an academic year behind their back and you gather, the nominations. I remember one year I nominated Brad Hattaway for the Cawthorne that he won, and I was very duplicitous. I needed references, and I'm not in his department, so I actually interviewed him on some teaching things related to gen ed reform, but the real point was to gather some reference names for students and things. So you have to be a little duplicitous, and thank you for doing that and making it such a nice surprise. And thanks to everybody, whoever they might be, that wrote such nice things in their letters, and obviously they had some teachers who taught them how to write. I'm really grateful to all of you, my colleagues. Most of you who know me know that without you, I would be worse than useless, you know. I mean, I think about these times when I'm in the math lounge, which is where I hang out most of the day when I'm not in a classroom, and when a student or students will wander in, like maybe it's Curtis Mann and Eric Mortberg, some 2014 grads, who came in one time and told me how they had modified Google's PageRank algorithm to address this problem in a national math modeling contest. And then went on to ask some questions in the foundations of probability and whatnot. Or maybe it was Sarah Sandman who, before class, really wanted to know what was so significant in Augustine's encounter with the Neoplatonists, and this kind of connected with questions of what the heck does it all mean anyway? Or maybe it could be Stanford Broadwater coming in to show this calculation of this really tough definite integral that David Bowman put up on the blackboard a few weeks ago. David is our retired physics professor who still posts problems, challenge problems, on the whiteboards in the halls of Ashern. And Stanford had employed these devious techniques to calculate the interval, and now he extend it. Or the other time he walked in last year, and he was really quite sure that Aquinas' second way argument for the existence of God had to be sound, because there's no such thing as an infinite causal chain. That's not possible. We'll address that. But so there are these moments, and in these moments, a thought kind of halfway forms that, oh, this is what I got into teaching for, But it never quite forms, because I realize this isn't teaching. This isn't even working, This is just like I'm hanging out with students in the math lounge or solving problems. Teaching is actual hard work, And somebody else did it with these students, It was probably Leverance who got them to become mathematicians in the first place when they weren't even sure they liked calculus, Or, maybe it was Hathaway to actually taught them how to argue cogently, or Barbara Birch doing that picky work you've got to do to get people to write in an organized fashion, That's the real teaching. That's the real work. That kind of early on work when the students aren't even sure about themselves. And that's the work that you ought to do. And that's what makes these moments in Asher possible for me. So I'm grateful to you for that. So I'm grateful to the students, who rise to moments like this, and who in their own ways have taken up and carried forward that tradition of liberal learning, I can think of particular students who've gone on to become teachers themselves, such fine teachers that their students come to Georgetown already prepared to rise to those moments, And so the tradition continues. I hope will always continue in these kind of ever-widening circles, beyond the life of any of us, beyond the life of Georgetown, beyond the life of liberal arts higher education as we know it, because I think in some sense the most gratifying, valuable exemplars of liberal education you see actually do occur outside of institutions. Think about the reading groups that take place at pubs. Think about, if you lived in an old Native American tribe, that maybe your uncle might take you out not only to show you how to hunt, but also make sure you got the lore right. Liberal learning can take place in all these kind of venues. And I'm very optimistic that tradition will always be with us. So anyway, given my debt to colleagues and students, it's clear, that the Cawthorne Award is not, at bottom, the recognition of any individual achievement. Not that I'm sharing the prize money, okay, because that got swallowed up in some deferred home maintenance. But I'll have you know that if you do visit, you're welcome to use the bathroom upstairs. It looks okay now, and you've richly earned it. Okay. But on top of that, and especially, I'd like to add my thanks to the Cawthorne family. I don't know if any members of the Cawthorne family are present. If you are, you don't mind making yourself known. For establishing this award and in stipulating, in addition to the nice prize money that gets swallowed up in all of our home improvements, that there be this, and this is the scary stipulation, that there be this lecture, because I think that's where the real value has come in over the years. I mean, these lectures, we've used them to tout the value of our respective disciplines. Like Pete Rue gave this master tout talk for music as his Cawthorne lecture, I still remember. Or people use it to sort of consider a particular problem in the discipline. So that's what Sheila did last year, with humor in religion. Or to think about some of the broader philosophical or theological implications of their discipline or questions that are raised by that discipline. We've tried that out too. And then once, but hopefully just that once, we did use it to reflect on the life and work of a colleague who passed away from us all too soon. But taken together, I think these lectures have really contributed something very rich to the inner life of the college. So thanks to the Cawthornes for making that possible. So when I speak outside of first floor of Asher, I seldom speak on mathematics for reasons approximately the same as when I'm, say, taking an airplane flight and you sit down and you strike up a conversation with the person next to you, and about 2-3 minutes into the conversation, he asks you, so what do you do? And you kind of want to say, I'm in roofing and siding, Because if you say I'm a mathematician, their face scrunches up, and 95% of the time they say, math was my worst subject in school, and it takes you like 10 minutes to get back on an even keel with them. For that reason, I usually haven't talked about math, when I talk formally outside of Asher. But I'm going to make an exception about that today. I need to do just enough math with you to enable me to articulate what I acknowledge is a very personal, but I hope not entirely singular, view of the experience of doing mathematics. I want to sort of open up to you maybe something that is not just experience of a practitioner, but something about the inner life of mathematics itself. But since there's math involved, let's warm up to it, okay? So I'd like you to have a look at this photograph. It's taken by a friend of mine. She's an artist, a model, a poet, kind of a moody, solitary person. She makes her day job is she runs like hostels, cheap hostels in big towns. In fact, we met when I was staying at a hostel in Tucson, Arizona, doing some of that immigration work the college would do during spring breaks. Anyway, she travels somewhat frequently and always alone. And here she is traveling in Bogota, Colombia, and seated apparently in some sort of cafe or coffee shop. And so imagine yourself there. And can you see, does it show up okay? You're at your table, and there's just enough sort of light from those overhead bulbs to kind of place you where you are. It's a calm setting, Here's your table. There's the bread basket in front of you. There's the cup of coffee, maybe still steaming. And you're looking out through that open doorway. And you're traveling alone. You know that kind of limpid, open feeling of traveling alone? You feel a little bit unmoored. you have to avoid. That's why they have those things in the airplane malls, with all the stores, the prices, because you're unmoored. You got to avoid them. That kind of limpid and open and restless and unmoored feeling, like there's that door, there's that bright light outside, there's this promise of some vivid life outside that door. I could walk through that door. I could walk through that door. But you don't. You don't. So that state you're in is called nowadays the liminal states, from the Latin word limen, meaning a threshold. Apparently, I had to read up on this, it was coined by anthropologists who were trying to describe these transitional ritualized experiences, say from childhood to adulthood. Often there'd be some kind of ritualized transition, and a very explicit acknowledgement that you're in a phase where you've left behind the old norms and social responsibilities of that previous state of life, and you're about to pick up new norms and responsibilities. So it's an original usage by these anthropologists. It was always for a transitional state. But as the years have gone by and people have been kind of captured by the romance of the liminal state, it's been applied sometimes to permanent social roles. So example, how about a shaman in an indigenous tribe who serves as a kind of a link figure between the mundane life of the tribe and the spirit world, perpetually in this kind of in-between, never quite having the roles and the responsibilities of either world, and always kind of peering into these other thresholds. Some people might even suggest entire societies could be liminal at their best. I mean, think about it. Since the Second Vatican Council, the Roman Catholic Church calls itself the Pilgrim Church on Earth, So liminal. And what I want to suggest is that the inner life of mathematics is this kind of permanent liminal state where you're peering into three thresholds: the threshold to science, the threshold to art, and the threshold to religion. So let's explore these. Threshold to science. Just a work by M.C. Escher there, an artist who's popular with mathematicians. You're inside a cubical structure looking out through archways at a moonscape, and there's something paradoxical about the way the views shift. You can look into it if you like. But in this exploration, and kind of in keeping with the idea of transitions, liminality, thought I would bring up maybe the Bridges of Knigsberg. This is a sort of foundational problem for a whole area of mathematics called graph theory. It was considered by the mathematician Leonhard Euler, Swiss mathematician from the 1700s. He took up a problem that the people of Knigsberg, apparently this old Prussian town, I think it's in Poland now or something, that they had concerning the layout of their town. There was a river that ran through the town, and this is a somewhat stylized representation of the river. And there were bridges over the river. So you've got there are 7 bridges over the river that divide the town into 4 regions, top and bottom and this little island thing, and over to the, let's call it the east. And the inhabitants used to wonder, is it possible, in fact, I'll just go ahead and quote Leonhard Euler on this. This all comes from a paper, Solutio Problematis ad Geometriam Situs Pertinentis, a solution to a problem pertaining to the geometry of location. And here's the way he phrases it. Could someone seek so as to plan his trip around the town so that he crosses over every bridge once and not more than once? Okay? He says, it's been reported to me that some people deny that it can be done. Others doubt it, and no one affirms that it can be done. But nobody really proved that it could not be done. And so he thought, well, how would you prove that it can't be done? Maybe you could make a complete enumeration of all possible, check every path and see that no matter what path you try, you're going to mess up. So let's try that a little bit. Like maybe you could start here, okay, and walk over this bridge and then this bridge, and come back and cross these two bridges, and okay, I guess your only choice now is to go on this bridge. And then I have a choice. Oh, but now I'm stuck. I haven't used this bridge up here once, you see? But I've used all the other bridges to this island already once, so I'm stuck, you know. So you could imagine trying to sort of find a way to list out all possible paths and just like check for each path that it won't work. It won't allow a circuit of the desired type. But that's much too messy. As Euler says, this method of solution, due to the large number of combinations, would be not a little difficult and laborious. That's how the Latin sounds, kind of ponderous, you know. But he has a larger concern. In many other problems concerning many more bridges, it could not be employed at all. Not that he wants to solve the problem for bridges and he wants a solution that actually delivers enough insight that it could apply equally well to problems regardless of size. Okay? So what's an insightful way of showing that no such trip is possible? If we're going to get some insight into the situation, we really need to remove the details of the situation that are irrelevant to the mathematical core of it. Okay? So let's think about this. Are the buildings important in the problem? Is it important that there's like a church up here or anything? That's not important. So just get rid of them, okay? It's just the regions, not the buildings in them. They're important. So we'll focus our attention, you know, on that. But there's more. When you're making your path through the town, does it really matter how you walk through a region from one bridge to another? Straight to get there as quickly as possible, or go around, visit some places? All that matters is that you went from the left bridge to the right bridge, right? That's all that matters. So the path on the landmass is not important. So why not just represent each of the land masses as a dot instead of a big spread out region that tempts you into thinking about irrelevant stuff? So I've got now 4 dots for the 4 regions, A, B, C, and D. And thinking a little bit further about it, the water's not important, is it? It's not important that the bridges go over water. You just want to walk over the bridges. So let's eliminate the water. And then all we really need is the dots that represent the land masses. Draw lines between the land masses, or the dots that represent them, and those represent the bridges. You see? So what you've got when you've taken it down that far, when you've cut out enough of those irrelevant details, is what we call a graph. And a graph is just a set of points that in graph theory we call vertices. And any pair of vertices could be connected by one or more or even no edges. Okay? So that's just a graph. Now, once you've got the structure to a mathematical graph, no longer a physical thing, a town, then you can turn your question about the trip into a mathematical question. The math question is it possible to make a path from vertex to vertex in this graph so that each edge of the graph is used exactly once? It would be called an Euler path in honor of Leonhard Euler. Now, thinking a little more about it, there are edges going out of. How many of them go out of a vertex? The number of edges going out of a vertex is called the degree of the vertex. And I'd like you to just take a look at the graph again and see if you agree with my list of the degrees here. I think the degree of vertex A is 5 because I see 1, 2, 3, 4, 5 edges coming out of it. Okay? And how about a B? 1, 2, 3. How about C? 1, 2, 3. How about D? 1, 2, 3. Okay. So there are the degrees. And by the way, notice they're all odd. That'll be important in a minute. All odd numbers. Now, next step is I want you to assume, not be, but just temporarily, for the sake of the argument, okay, that an Euler path does exist for this graph, okay? You don't have to know what it is or have a picture of what it is or believe that there is such. You're just assuming temporarily there is for the sake of the argument. Got that in your mind? Okay. Let's think about what might happen along that path. I'd say along that path there would be three types of vertices. There'd be a start vertex wherever you start, right? There'd be a stop vertex wherever you stop. Now that could be the same as your start vertex. You agree? You're making a quote-unquote round trip? Yeah. And any other vertex that's not a start vertex or a stop vertex, let's call that a pass-through vertex, okay? And I want to focus in on those pass-through vertices right now. So let's say X there is some pass-through vertex in a graph that's got an Euler path, and let's say you're taking that Euler path, so you're going to pass through that vertex. So that means you got to come into it at some point. But since it's a pass-through vertex, don't you have to go out of it too? And so maybe you'll go out to some different point. You could even go out to the same point. But you got to go out. And then maybe you'll come back in again. But if you come back in again, you've got to go out again because it's a pass-through vertex, right? Are you noticing that the vertices, or that the edges that you take, are going to come in pairs? A yellow in and a red out, and they make a pair? So like if you're done with that pass-through point, you're not going to come in again, the degree of that point must have been 4, right? Because you're using all the edges once and only once, so those are all the edges that come out of that pass-through point X, 4. And you know, I could imagine more complicated pass-through points that you come in and out of more times. But no matter what, do you see that if you're a pass-through point, your degree has got to be an even number because of the pairs. So you look back at this Knigsberg graph, and all of these points are D. So I think you know where we're going with this. All 4 vertices in that graph have to be start or stop vertices because they cannot be pass-throughs, right? But you can have at most 2 of those. If you have a stop that's different from the start, that's at most 2. So at one and the same time, if there really is an Euler path through this vertex, then at one and the same time it is true that there are 4 start and stop vertices and there are no more than 2 start and stop vertices. That is a contradiction. Contradictions can't be true. So there must be some problem with the assumption that there's an Euler path at all. You know? That's the proof that nobody before Euler actually had, that there is no path through the town that uses each bridge once and only once. And Euler went on in the paper and he proved, talking about kind of the bigger graphs, he used this insight to prove that any old graph that you take at all, no matter how big or small, it'll have an Euler path if and only if the number of vertices that have odd degree is either 0 or 2. So he had a pretty general result that could be applied to all kinds of bridges, towns, whatever. So I want to really emphasize that crucial step of getting rid of the irrelevant details and coming down to the mathematical core of a situation. We call that modeling. You take the physical situation, you turn it into a math situation. The physical situation problem becomes a math problem that you can then address with computation and logic. You get an answer, and you can translate that answer back into the physical situation. No, folks, you can stop. You have to keep trying. There ain't no way. You know. That's the core. That's the threshold of math to science, because it all happens through modeling. So just in graph theory, just in the graph theory part of math, using graphs, we model things like traffic flow along roads and highways to try to, make routes that allow people to get to places faster on average. Or we model the flow of information on the internet through graphs. We modeled the organization of data in computers with graph theory. Chemists actually use it to study the behavior of crystals. Physicists use it to solve problems in statistical mechanics. Social scientists are now starting to use graph theory to analyze actual real-world social networks. And just last couple of months, I used graph theory to help design this big online database for the study of basically how people pick up languages, and they needed a big database that compared speakers that say a sentence in a foreign accent versus a native accent, and there had to be like a way of doing the pairing of the speakers that's kind of unbiased, and there's thousands of speakers you had to work with. Anyway, graph theory helped. So that's going to come out, I guess, next year. That's done with 2 psychologists at Eastern Kentucky University. So it goes on in big ways and in small ways. And that's just one tiny area of mathematics with these big modeling implications. So that's the threshold to science. Mathematicians aren't scientists. We don't think like scientists. We don't act like scientists. We're moody and artistic and other things. We really are very different in personality from scientists. A mathematician can also be a scientist. Act as one. They really aren't doing so qua mathematicians. They may be using mathematical tools to model, but it's a very different feel. Mathematicians always take a scientific situation and they pare away a lot of what you think of as what the science is really about and for. Next threshold to art. Stanford Broadwater actually turned me on to this book because he brought it to the office one day last year. It's Fantastes by George MacDonald, who was like an early exponent of fantasy literature for adults. He's like the grandfather of people like C.S. Lewis, Tolkien, and so on. And this is an illustration from his book Fantastes, where the protagonist, Anodos, which means he who has no way, is being kind of forcibly shown the way into fairyland because his bedroom kind of turns into the stream that leads into fairyland. So he's waking up and he's about to head into fairyland. Mathematicians are not artists, but they are aesthetes. We have a very strong, highly developed notion and sense for, a nose for, beauty in proofs. You mathematicians describe a proof, like that argument that we just did with Leonard Euler, as elegant or deep, or in pejorative tones, I might say that's clumsy, that's technical, that's messy, And so we have these notions. And in mathematical theories, so a mathematical theory is a set of statements that you prove concerning a certain class of mathematical objects. So graph theory is an example of a mathematical. We even have aesthetic ideas about theories, like the theory of C-star algebras and functional analysis. The structures there are very complex and they're endowed with many properties. It's a rich theory, we say. Or several complex variables. That's an elegant theory. And the people who do several complex variables, they're elegant people. I mean, the personalities really match up. Combinatorics, graph theory could be thought of as a part of that subject, is considered lean. The number of techniques available are kind of relatively small because the structures are relatively simple. The use of them is great, clever, and extended. Lean theories. So these are the cross-country runners of mathematics. And the personality actually often matches. Mathematical logic, which was my concern in high school and college, unfortunately is called a hairy theory. The proofs are almost always technical and messy. Although the results are profound and illuminating and numinous, the proofs are almost always something you just have to fight through. So I'm sorry about that. But through it all, the sense of beauty really is coming from the existence of and the possibility for proof of an answer in the way that Euler proved such trip is possible. And the recognition of the importance of proof is just throughout the history of mathematics in all kinds of cultures. So here's the mathematician Bhaskara writing in the 12th century in the Siddhanta Shiromani, which is this is a very puffily named treatise. That means the crest jewel of comprehensive treatises on astronomy. And he's about to launch into a consideration of the sphere, the geometrical object, the sphere, that is going to be used to justify various astronomical. He says, you know, you got to study this, folks. He says, a mathematician, knowing only calculations and not their demonstrations, will not attain greatness in the assemblies of the eminent, and will himself not be free from doubt. And he goes on, and he says, you know, a clear demonstration is perceived directly like a fruit in the hand. And he's speaking especially of proofs that have a geometrical flavor, almost visual flavor to them. And the moment you get them, kind of that moment when you saw something was up, all the points had to be, you know, none of the points could be passed through, all that kind of stuff. That moment when something is up, it's perceived directly like a fruit in the hand. We live for that experience. It is a timeless kind of experience. It's like there you were looking at the possibility of having to go through all those enumerations of all those different paths, all their particularity, all their branching complexity, waving around, you know, in your head and confusing you. But with the insight came this moment of like suspension of all of that particularity and contingency. It's still there, comes still, you know, and elevated into vision outside of time. It reminds me of what John Keats said in that famous poem, Ode to a Grecian Urn. This is not the urn he was necessarily looking at. It's similar. So we know that the urn he's looking at, there is a tree, kind of like the tree you see here, but there was also a pair of young lovers, one chasing the other through the little fields, you know? And that action is captured on the urn. And he looks at the stillness of the urn and he says, thou still unravished bride of quietness, thou foster child of silence and slow time, sylvan historian who canst thus express a flowery tale more sweetly than a rhyme. Ah, happy, happy boughs that cannot shed your leaves, nor ever bid the spring adieu, and happy melodist, unwearied, forever piping songs, forever new. More happy love, talking about the couple chasing each other around, more happy, happy love, forever warm and still to be enjoyed, forever panting and forever young. So all of the kind of the rush of the warmth, the lust, you know, captured in stillness and suspended in a view. When old age shall this generation waste, thou shalt remain in midst of other woe than ours, a friend to man to whom thou sayest, beauty is truth, truth beauty. That is all you know on earth and all you need to know. So, actually, I want to borrow and modify a phrase that I found in Fantastes, the book that Stanford was reading. I would like to say that beauty is not the standard and guide to mathematical truth or truth in physics. You know, we often consider a theory to be, we wish it would be true because it's so pretty, you know, but we all know beauty is not the guide to truth. Truth is not unlocked by beauty. And yet, it seems that deepest truth is deepest beauty. That's the experience that you get in this kind of the elevation of the insight and that timeless vision, that there is no separation between the truth of what you've come to through the hard work and the beauty of it, you know? So just to recap a bit, the experience of insight and proof for us, yes, it's about removing doubt. And yes, 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 it is about that you see it for yourself, you know, fruit in the hand, elevation of vision. But I want to add one more thing. It's empowering. And I mean that in a very different sense from being powerful. You know, I hate it when people tell students that they have to study math to get a good job, you know, because math is so useful out there, you know. I hate it when people do that because partly it's because it's an exaggeration. It's a total exaggeration. Math is not that useful. Less and less useful these days as the very computational tools that mathematicians have designed are doing more and more of the kind of computational math that needs to be done. There's actually that job that directly involve a lot of like creative math problem solving that has to be done, not directly. So it's exaggerated, but it's also just wrong-headed. It's not about power. It's about empowerment. And I was thinking, how could I express this? And it occurred to me, there's a story. I was at a math conference about 12 years ago, and there was a session on liberating pedagogy. So the presenters are bringing forth the works of Paulo Freire. He's this Brazilian liberation theologian and educator. So a lot of mathematicians aren't familiar with the material, but they're being asked to consider, is there a way that you could teach mathematics that's in line with these kind of liberating social justice principles? And so in the question and answer discussion afterwards, we were considering this. Could the mathematics be made relevant to things like social justice? And one elderly mathematician got up in the back. And he was it doesn't have to be made relevant to social justice. It is justice. And the organizer of the session was like, oh, well, how so? And so he told the story of growing up in a one-room schoolhouse during Jim Crow segregation in, I think it was Tennessee. And he said, you know, our favorite subject every day was math. English, it was all white authors. History, it was all about slavery wasn't so bad. And in Tennessee, they treated their slaves well. It was all stuff that kind of the white world produced and approved and dumped on you. But math wasn't white. Could not be. And transpersonal, almost transhuman ability to check things step by step in proof that exists in mathematics. The self-containedness of it keeps dominant powers from being able to harness the subject matter to glorify themselves, justify themselves. So it was a level playing field, he said. Anybody could do it. Anybody could give it a try. Anybody could achieve. Anybody could rise to that level and experience that insight for themselves. And so I've often thought back, about what he said, because what must it have been like, if you had solved some complex algebra problem and you could justify it, not just do the calculations, but demonstrate step by step that your solution is correct. You're holding that fruit in your hand. And no white person could come to you and say that you had not achieved that. I mean, they could try, but you would know for yourself that they were wrong. Imagine the confidence with which you confront the world from that kind of achievement. And his remarks really resonated with everybody in the room, because most of us hadn't grown up in that particular situation of racialized marginalization or whatever. But that experience of being young and not knowing your footing yet, but maybe finding the confidence to front the world through achievement in mathematics was something that most of us did share. Again, very different from power, because it's an experience of empowerment. Yes, you're holding that fruit in your hand, but you know that moment was mediated through teachers and guides, and that it came through a kind of an alignment with a reality beyond yourself, a disciplined alignment with a reality beyond myself that I'm dimly brushing up against, but I can't quite articulate. And so it's not like my power like a superpower that I get to use for whatever I want. It's different. It's empowerment. drifted a bit from the threshold to art, and it may be knocking up on the threshold to religion. So this is just a picture of looking out from the meditation part of the temple at Furnace Mountain, which is a Zen retreat center about an hour east of us. And you're looking out through an open door over the mountain they call the Purple Dragon. I should have warned there will be Sanskrit. This is a little snippet from the Brihadaranyaka Upanishad. Again, great title, The Hidden Connection of the Great Forest. And it's just a little snippet that occurs at the beginning of the 5th chapter. There's like no context for it, and it's not clear to me that the chapter actually addresses this verse that is at its head, but it's in this ancient text, and it's become very popular as a chant or a mantra in Hindu culture. So with Old Town Road, that I would chant it for you, okay? Purnamada Purnam idam Purnat Purnam udachyate Purnasya Purnamadaya Purnameva vashishyate. What does it mean? This is the literal translation. That is the full. Purnam, the full, is that. Arha. This is the full. Purnam idam. From the full arises. Having taken the full from the full, precisely. And it's interesting that in many modern translations, the Purnam full is often translated the infinite. And I'd like to explore why that's a popular kind of interpretation of this ancient verse that we really know very little about. So, to do that, we need to get more concrete. How many blind mice are there? 3? Yeah, no trick question, 3. How do we know there are 3? Don't we do something like this? 1, 2, 3. What we do is we pull out our fingers and we match up a finger with a mouse, a separate finger with another mouse, a third finger with another mouse. We're out of mouse, so we stop, right? And we say there are 3 mice. So implicitly what we're doing is we're saying there are 3 mice because the set of blind mice up there can be put into a one correspondent with the set of natural 1 and going up 3, okay? That's how you count things. That's what the size of a thing is in mathematics. 2 sets are said to be the same size if you can put them in one-to-one correspondence with each other. So this set of triangles is the same size as that set of hearts. I know that as soon as I make this correspondence here. It's one-to-one, meaning no 2 triangles went to the same heart. It's also onto all the hearts got caught. You know? As soon as you make just one of those correspondences, you know those 2 sets are the same size. There's actually several more correspondences you could make, but you only need to see one. You know they're the same size. That's how you count sets. Do you all agree? That's actually how you count sets when you think about it. Okay. So back in middle school, Mrs. Erickson popped this up one day in the classroom. She said, here's the natural numbers. And here's the even numbers. And she says, are those 2 sets the same size? And we're all like, no, right? Because, I mean, look, the even numbers here, that's small. It's missing all the odd numbers, you know? Sets are not the same size. And she said, well, but, look at this. What if you decided to set up a correspondence between the even numbers and the natural numbers by simply dividing every even number by 2? Wouldn't that be a one-to-one correspondence between the 2 sets? So the 2 sets are the same size. Take the even numbers from the natural numbers. The odd numbers remain, right? But look at the odd numbers. Here, look at the natural numbers. Are those two sets the same size? Yep. All you got to do is take each odd number and maybe do twice the odd number minus 1. 2 times 1 minus 1 is a 1. 2 times, what is that correspondence? Let me think about this. Oh, half the number plus a half. That'll do. Yeah. So like half of 3 plus a half would make 2. Half of 5 would be 2.5 plus a half would make 3. Yeah. So those two sets are in one-to-one correspondence. So look at this. Look at what's happening here. This is infinite. It's natural numbers. And having taken the infinite, the even numbers, from the infinite remains. Having taken the full from the full, precisely the full remains. And I should point out that you can take actually a lot more than that from the full. So if you're interested, you could explore this. Aren't there infinitely many prime numbers? That actually can be proved, but we won't need to go through it. There's infinitely many prime numbers. And I would like you to look at the powers of the prime number 2. So 2 to the first power is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16, and so on. Would you agree it's an infinite set of numbers? Okay. I'd like you to look at the powers of the prime number 3. 3, 9, 27, so on. Would you agree that's also a set of infinite numbers? Or an infinite set of numbers? The powers of 5, also an infinite set of numbers. Powers of 7 is an infinite set of numbers. The powers of, what's the next prime number? 11? Yeah, an infinite set of numbers. So what I've got here is every prime number corresponds to a row of numbers, an infinite row. And so there's infinitely many rows because there's infinitely many prime numbers. And you know what? No two of the numbers on that infinite lists are the same. So think about it. So if you think about it, inside the natural numbers, this infinite set, is infinitely many different infinite sets. And you could take them all out. But what would be left are the numbers that are not a power of a prime. And that's a lot of them. That's infinitely many of them. So you could take infinitely many infinite sets out of the infinite, and still the infinite remains, you know? And that's not the only thing. It turns out that as grand as this makes the infinite look, the size of infinite we're talking about here is actually the smallest possible infinite size. There's actually infinitely many infinite sizes that are larger. And, well, there's more. Well, I can't even say. Like, it's even a math theorem. You can't say how much more. And all of that was Cantor in 1870. But the big thing was this like middle grade idea that you could take the infinite from the infinite and the infinite remains. Think about that in relation to how we think about God. Think about, what is it, Psalm 42? You know, deep is calling on deep in the roar of waters. You know? Or this conversation that my old had with his 5-year-old nephew once. His nephew comes up to him and says, "Uncle Dan, God goes on and on forever, right?" And he says, "Yeah." "And God lives in us, right?" says his nephew. "Yeah." "So we go on inside forever and ever, right?" You know, something of that intuition that we have these boundless depths that they are related to either by creation, if you're a Western Christian type, or emanation, if you're more of an Eastern type, related to some primal infinity, which gives infinitely of itself so that you may be manifest and yet remains infinite. That may be why that math fact was considered luminous, got manufactured into this old Upanishad chant. Able to track down classical commentaries that actually address the meaning of that chant. It's just a common thing you can sort of see in modern 20th century and later that interpret it that way. But I find that just very, very numinous and interesting that there's so much in mathematics that gives you that feeling but you're kind of brushing up against something numinous and beyond yourself. And yet there's nothing in it that gives particular aid and comfort to any one religion, maybe Neoplatonists. Yeah. So like that's the life of a mathematician, kind of like forever suspended, between science and art and religion. And maybe you could reflect for yourself, with your own particular discipline, ways that you are also suspended between different worlds. Because I said this is a highly personal vision, but I don't think it's quite singular. Thank you. Yeah, go ahead and. We only have about 5 minutes, right, before people need to get going.
Anybody? I've got one.
Yeah.
Does math really exist, or is it just a description?
The famous analytical philosopher